Welcome to Unit 4. Last time we started modal logic and got into translations, and today we'll do a few translations and then we'll start to do proofs. And before doing this unit, again, I suggest that you do a few of the translations and read ahead and do the logicola part on translations, because then you'll be all prepared for today. Okay, review a little bit. Modal logic builds on propositional logic, so you have like capital letters for whole statements, squiggle for not, or is a V, and so forth. S rules and I rules and proofs and the whole thing. You have two new symbols. You have and these are for possible and necessary. So possible is a diamond, and this holds for things that are logically possible. That is, there's no self-contradiction. They needn't be physically possible. And another way of saying it's possible that A is true in some possible world. For example, it's logically possible that I could run a mile in 2 minutes. It's not physically possible, but there's no contradiction in the idea. And another way of saying that is that you could imagine a consistent story or a possible world in which that happens. Probably not a real exciting story, but, well, there you go. Necessary is a very strong claim. It says not just that the thing is true, but that it has to be true. So possible is weak, and it doesn't even say it's true. And necessary is a very strong claim. And another way of saying necessary is true in all possible worlds. And we got last time into different translations. For example, A is consistent with B. Means it's possible that they're both true together. A logically entails B means it's necessary that if A, then B. And then we have ways of translating consistent statement and consistent truth. And then I had you do some of the logicola problems for that, for the translations. So here we go. I had you do some homework ones from the book. And now we'll go into the translations here. 15 says if A has an all-one truth table, if B has an all-one truth table, let's say T, then B is inherently necessary. It's necessary B. So if B has an all-one truth table, then it's inherently necessary that B. 16 says necessarily if there's a God, then there's no evil. This is not ambiguous. The box is on the outside. You know, if the first thing is necessarily, then the box begins the whole thing. 17 is an ambiguous one. Which are ambiguous? The if-thens, where the then part has a strong modal claim, necessary or impossible. And this could mean, box outside, it's necessary that if G, then not E, and that's the same as the one before. Or it could be box inside, if G, then necessary, not E. Okay. And this one you could also write G implies not possible, E. So these are two that really the same thing. So it could mean two different things, this and this. And the second one you could put necessary not or not possible. Then 18, if there must be matter, then there's evil. Again, you follow the the English word order there. If must be better than evil. 19 says necessarily, if there's a God, then there's evil. Taken by itself as self-contradictory would be not possible, E. Or you could write that necessary, not E. It's not ambiguous. It's just there's two different ways of writing it. Then 20 says it's necessary that it's heads or tails. Let's say you're flipping a coin. And I suppose it could be that it lands utterly balanced between the two, but if we ignore that, it's got to be that it's heads or tails. And 21 says either it's necessary that it's heads or it's necessary that it's tails. So, which one makes the stronger claim? Well, it's 21, and 21 says one or the other is necessary. It might be this necessary, this heads or tails, without either side being necessary. In fact, this one suggests that the coin is kind of fixed, that it's a cheating coin. Okay, how do we do proofs in modal logic? Well, something like propositional proofs, except we have four new inference rules, and we also have possible worlds. And a world prefix is a string of 0 or more instances of W's, and these represent possible worlds, or ways things might be or might have been, or kind of like consistent stories. So a string of 0 W's is a possible world, a string of 1 W, a string of WW, a string of WWW. So these are all different ways things might have been. Maybe World WW is the one where Michigan won the national championship, not just last year, but for the past 20 years in a row. That would be a very nice possible world. And this might be a possible world where, maybe Ohio State won it 20 times in a row. Very bad possible world. So these are different possibilities. The blank world prefix represents the actual world, the way things are. Okay. Now, how do you use these W's, these strings of W's? Well, a derived step and an assumption. That's how you use them in derived steps in a proof and assumption. Not much in assumptions, a lot in derived steps. So you can have, therefore A means A is true in the actual world, and this is a world prefix consisting of 0 instances of W. So the old derived steps, like therefore A, are derived steps on this new definition. Therefore, A is true in world W. So you would write W, therefore A, or therefore A is true in world WW. It would look like that. Okay. Oh, pardon me. I am dying. No, not quite. Not quite. Now, the inference rules that we've been studying work as long as you keep everything in the same possible world. So if you have A and B in a world, well, therefore A is true in the world and B is true in the world. And if you have it true in world W, then A is true in world W, B is true in world W. So you got to keep, you can use all the normal inference rules as long as you keep everything in the same world. Now there's a couple of rules for going between worlds we'll see, but we'll get to that in a moment. You can also use W's in front of assumptions. A normal assumption looks like this. Assume that A is true in the actual world. Here's where you would assume that A is true in world W, or you might have two W's, assume that A is true in world W. You won't use this a whole lot. The only time you'll use it is when you need to make an assumption to break up something in another world. That's with multiple assumptions. How do assumptions work with these? Well, let's see. I don't have much room to write here, so I'm going to write big and fat. Let's say that you make an assumption A, and you get a contradiction. You get B, not B. You can block it off and conclude the opposite, not A. Okay. Now let's say that you assume A in world W, and you get a contradiction anywhere. Then you conclude the opposite in world W. Okay, so how does reductio ad absurdum work in modal logic? Well, if you assume something in a world, you get a contradiction anywhere. It doesn't matter where the contradiction is. You can conclude the opposite in the same world where you assumed it. Okay, now what is it to get a contradiction? Well, you need a letter and a formula ends to nil in the same world. So you need like B and not B in the same world. If you have B in world W and not B in the actual world, you get no contradiction. They need to be both in world W, or both in the actual world, or both in maybe world WW. So how does reductio ad absurdum work in modal logic? Well, you assume something in a world, you get a contradiction anywhere. Doesn't matter. And a contradiction is a formula and its opposite in the same world. And then you conclude the opposite of the assumption where you assumed it. That all sounds sort of complicated, but don't worry. Once we do a few examples, the whole thing will make a whole lot more sense. Okay, now there are 4 new inference rules for modal logic, and the first 2 are called reverse squiggle rules. If you have not necessary A, you get possible not A. They do mean the same thing. You say it could be that A is false, and it's not necessary that it's true. Same thing. So if you have not necessary A, you can convert that to possible not A. Similarly, if you have not possible A, you can convert it to necessary not A. These mean 2 different ways of saying the thing is impossible. So not possible A gives you necessary not A. Now, to work these, the not box or not diamond has to begin the whole thing. The rest of it could be a much longer formula, but this has to begin the whole thing. And then you switch it not necessary to possible not. Okay, there you go. Now, the strategy here is to use these 2 rules first. If whenever you have not necessary, change it to could be that it's false. Or not possible, change it to it's necessary that it's false. Do that right away. The strategy is to use these so that the formulas begin with the box or the diamond, and then you can drop them into worlds, and then you get a contradiction. So the first thing you want to do is reverse squiggles. If you have not box, not diamond, begin the whole formula, you switch them to these. And then you can start the step and henceforth forget it. Generally, the second thing you do is drop diamonds. Possible A means A is true in some possible world. So you give the possible world a name. So let's say it's necessary that it's heads. Or it's possible that it's heads. Therefore, you imagine a possible situation, possible world in which it's heads. Okay, so possible means it's true in some possible world, and you give it a name. Now, every time you drop a diamond, you got to use a new string of W's. So suppose you have, it's possible that it's heads, and it's possible that it's tails. You got to drop each one, but in a different possible world. It's possible that it's heads, so you imagine a possible world W in which it's heads. It's possible that it's tails. Oh, pardon me. So you imagine another possible world in which it's tails. See, if you say it could be this heads, could be this tails, it doesn't mean that they could be at the same time. So this is like one story in which it's heads, one story in which it's tails. So every time you drop a diamond, you got to use a new world. Okay. I made a very corny saying just so that you might be able to remember that. I call this the Christopher Columbus rule. After Christopher Columbus, who said it's possible to go to a new world. Okay, you get that. Possible new world. So if you have two possibilities, each one's got to go into a new and different world. And finally, and you can start the step because you haven't lost any information. If it's possible that H and saying H is true in a possible world, you haven't lost any information there at all. Getting rid of stuff here. Okay, so you do these two things first. You reverse squiggles and you drop diamonds into new worlds. Lastly, you drop boxes. If it's necessary, it's true in all possible worlds. So if you have necessary A, you can put it in world in the actual world without box or diamonds. You can put it in world W, you can put it in world WW, put it wherever you want. Sort of like a trump card. So what's necessary is true in all possible worlds. But you don't want to go into new worlds. You want to use the old worlds. And this one you don't star because you've never exhaust a necessary. These two, if you say it's not necessary that A, therefore it's possible that A, you haven't lost any information. And if you say it's possible that A, so possible world W, A is true, again you haven't lost any information. Here you have, if you say it's necessary that A, therefore world W has A true, you haven't exhausted it because it's true in every world. And so it'd be in WW, 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 and so forth. Okay, so those are the four inference rules. Use these to put the box and the diamond in the initial position. Then you drop initial diamonds. You can only drop initial operators, the diamonds and boxes. And then the last thing you do is drop boxes. And these, when you use, you can start and henceforth forget it. Now this is all very abstract, but it works kind of cool once you get to examples. Here's an example. It's possible that A and B are both true, therefore it's possible that A. Okay, that seems valid. How do you do a proof? Well, first thing you do is assume the opposite of the conclusion. So you want to prove it's possible that A, so you assume not possible that A. Okay, that's just like before. In the inference rules for modal logic, you first of all reverse squiggles if you can. Now, so if you have a not possible, you change it necessarily false. And if you have not necessary, you change it to possible false. Okay, that's using these two rules. You want to do that first. So not possible A gives you necessary not A, reverse squiggles. And then usually the next thing to do is drop initial diamonds using a new world each time. So we have this, it's possible that A and B are true together. So you imagine a possible world in which A and B are true together. So it's possible, this is possible, therefore it's true in a possible world. And this is okay because W is a new world. So reverse squiggles, not possible, therefore necessary, not. Then drop diamonds, this is possible, therefore it's true in some possible world. And then here you can just break it up. In possible world W, A and B are both true. Therefore, in possible world W, A is true. Therefore, in possible world B is true. Again, the old inference rules you can use in any possible world so long as you keep them in the same world. So in this world, you have the conjunction A and B. Therefore, you have A. Therefore, you have B. The last thing to do is generally drop boxes. You drop each initial box once for each old world. Never use a new world when you drop a box. Always use the old world. So you got a necessary not A. So where are you going to put it? In world W, not A. So, and if you had a world WW, you'd put it there too. You'd say it's necessary, it's true in both worlds. But here you just have one world. So then you get a contradiction. A, not A. So the assumption leads to a contradiction. That is, you get the formula and the opposite in the same world to get the contradiction. And so, therefore, the assumption is wrong. You conclude the opposite. So the general strategy, reverse squiggles first, not possible A, therefore necessary not A. Drop initial diamonds using a new world each time. So you have possible A and B, therefore in possible world W, A and B. And then you simplify this. And lastly, drop each initial box once for each old world. Here you just have W. So the initial box, every world has not A, therefore W has not A. You get a contradiction, you prove it valid. And there you go. That's our first proof. Let me do another example, and then I'll give you some to do. This is really, really easy, but it brings out a new element here. A is true, therefore A is possible. Okay, assume that A is not possible, so you assume the opposite, not possible A. And then we do what? We reverse squiggle, not possible, therefore necessary, not A. We can star that. We don't have any diamonds to drop, so we got to drop the box. Necessary that not A. All worlds have not A. Therefore, the actual world has not A. And there you go. So the box holds for all possible worlds. And so you can dump it in any world with W's or not W's. And then you have a contradiction. So the assumption leads to a contradiction, therefore wrong, and you conclude the opposite of the assumption, your original conclusion, and there you go. What's the difference between this one and this one? Well, here, when you drop the box, you put it in a world with W's. Okay. Here, when you drop the box, there weren't any world with W's, so you put it in the actual world and got a contradiction. So when you drop the boxes, what are the rules about that? In principle, you can put it in any world. Necessary A means A is true in all possible worlds, so you could put it in the actual world without W's, or world W, world WW, world WWW, whatever. So our strategy will be this: to drop a box into all world with W's. So if you have a world with W, put it in. And sometimes you drop it in the actual world. But often it's not going to help you like this one. There's nothing else in the actual world to contradict. So when do you drop in the actual world? In two cases. if you have an unmodalized instance of a letter in your original premises or conclusion. And that's the case there. You got the A without boxes or diamonds. It's unmodalized. So that's a sign that when you drop boxes, you got to put in the actual world too. Or you've done everything else possible, including further assumptions, and have no other worlds. You have no W worlds. Then you got to put in the actual world. That's true here. You know, reverse squiggle, you have no diamonds to drop, you get no world W, so you got to put in the actual world. So those are the two cases. You don't want to just like always, when you drop a box, put in the actual world, but just if either of these applies. Okay, let me give you 3 from the book to do. These are 3, 4, 5 on page 238. Why don't you do these on paper, and then, well, hit pause now, do them on paper, and when you're done, hit play, and I'll show you how to do the proofs, and we can see if you got it right. So, hit pause, do them, and then hit play again. Okay, how does this one work? These are all valid. We haven't gotten to the invalid ones yet. We'll get that a little bit later. It says, not possible that A is true and B is false. Therefore, A logically entails B. That works. That's valid. How do you work it? Assume the opposite. Not necessary. If A, then B. Then what do? Well, reverse squiggles, right? Not possible, you got to change to necessarily false. Not necessary, you got to change to possible false. So you got to change this one. Not possible, therefore necessary not A and not B. And then this one, not necessary, you change to possible not if A, then B. Okay, so you've reversed squiggles. We can start the steps then and ignore them. And then which do we drop first? We drop the diamond. So reverse squiggles first, drop diamonds, and then boxes. So we say, therefore, in world W, you have not if A, then B. And then if you want, you can simplify that, false if then. Therefore, first part true. Therefore, second part false. And then the last thing you want to do is drop the box. So all worlds have that. Therefore, world W has that, not both A and not B. Here you wouldn't want to drop it in the actual world. There's no benefit there. And then these two together will get a contradiction. So they're not both true. The first is, so the second is not. So we have B in world W. And then you have a contradiction. So the assumption leads to a contradiction and is therefore wrong. And we conclude the original conclusion. It's necessary that if A, then B. Valid! And there you go. Okay, so we begin by blocking off the conclusion and assuming the opposite. So not possible, not B. And then we reverse some squiggles. Not possible, we could say therefore necessary not B. But it's really easier just to say therefore necessary B. And I'll allow that. And then you have not necessary A, therefore possible not A. And then you can star that. Okay, so then you drop the diamond in a new world, W, where you have not A, every world has B, so you have B in that world, and then every world has A or not B, so you have world W has A or not B, and then you say at least one is true. It's not the first, so it's the second, so you have W, therefore not B. Then you have a contradiction, so the assumption leads to a contradiction, therefore wrong. So you conclude the opposite. And there you go. Again, valid. And then the last one I had you do, this is kind of a little trickier. If you assume the opposite, not possible, A or B, and then you can say, therefore, necessary, not A or B. And then there's kind of a confusing part, because you don't want to drop the box. You want to do that last. You want to drop the diamonds, but you can only drop an initial diamond. You can't drop a diamond which is inside of the formula. So you're kind of stuck, confused, bewildered. You want to drop this first, but you can't. So what do? Well, remember when we had multiple assumption arguments? I said when you're stuck, bewildered, confused, you break something, you make another assumption. And that's the key here. You need to break this by another assumption. If you get that insight, the rest of it's kind of easy. Suppose you want to break this. Well, you could take either side and assume it, or it's denial. So let's say we assume possible A. Okay, and then we can say, therefore, in world W, you got A true, star, star. Then drop the box in world W, not either A or B. So you get not A. Ooh, contradiction. Okay, so if you assume A, possible A, you get a contradiction. Therefore, not possible A. And then you can use it up here. At least one is true, but it's not the first, so it's the second. So you get possible B, and then you could put that in a new possible world, WW. You have B, because W is already old. You got to use a new world. Actually, though, if you don't, it's not a real big deal, because this is all blocked off, so it's really out of the picture anyway. So, okay, so in world WW you have B, and then the necessary thing you can also drop in that same world WW. You get not either A or B. Getting a little sloppy here, I'm sorry. So not either A or B, therefore in world WW you get not A, world WW you get not B. Contradiction, we have world WW with B and not B both. So now you kill your first assumption and conclude the original conclusion. Oh God, am I getting sloppy. Therefore A or B, and there you go. And again, it is valid. So, homework, do a few more translations, just to keep sharp with that, and 5 English arguments, and these are all valid, and read ahead. And this is about the invalid arguments or refutations. And Logicola, this is modal proofs valid only. We'll learn the invalid ones next time. Okay, so do that, and then we'll be all ready for the next unit. I'll see you then.